Hello, thanks for joining in this last briefing today. I'm going to talk about reverse engineering at bug hunting on this particular class of drivers in Windows, which is KMDF. This is my first time in 44Con and in London, so I'm very happy to be here. Well, I'm a senior security consultant at IOActive. And well, that's my Twitter handle right there if you want to connect. So what I'm going to talk about here, it's not really based on exploitation. I'm going to put the focus on how to find bugs in this kind of drivers and what are the interesting functions that we want to look at. This is not a full reference, of course. You have the MSDN for that, and the actual source code of KMDF because it's open source now. And why? Well, the thing is, I had this project for an OEM several months back, and we were tasked to look at the driver package of one of the latest laptops that they have. And I found several bugs in the KMDF drivers. The bugs were really easy to find, and some of them were in components that date back in 2012. So I think that was interesting, and I decided to, make a summary of everything I learned through that. These are some of the bugs that I reported since then to some vendors. You have a Intel camera driver, touchpad drivers from ALPS, Synaptics. The ALPS is really bad one. There's also one named Elan, it's not listed there. And these are used by different OEMs and modified by OEMs before they are put into your laptops. So you probably have some variation of this, but the base code is probably one of these. Another one's Intel wireless display, some bus drivers from Microsoft, and some gaming devices as well. All the gaming devices, like gamepads or joysticks, or even headphones, those probably deploy KMDF drivers nowadays. So are mostly used for bus drivers or hardware device drivers. So I will do here a quick recap on how WDM works for people that never played with drivers before. Then I'll just enter fully into KMDF. I highlight the interesting functions, common errors, and we end with some conclusions at the end. I have some demos to show. So hopefully you are entertained. So in Windows, you have different driver models. The first and base one is the WDM, but you have a bunch of them. KMDF is just another model that runs on top. It's an abstraction. But you also have WDDM, which stands for graphics, and this, which is for network, have file system type of different models of file system types. The idea is that in order to approach each one of these, you need to understand the model. Of course, it's 90% understanding the model and 10% of reverse engineering. That's how it is in Windows. So starting with WDM. This is the standard for all. All the other models use this one under the hood. And you need to understand this model even if you're actually programming in KMDF or WDDM or anything, because that's the way you get most of the driver model you're actually developing on. And if you don't understand this, you will probably have bugs anyway. And for software drivers, meaning drivers that are not actually managing a device, this is the model that still most vendors are using. So what's a driver? Well, a driver is just code that it's loaded into kernel space and executed with ring 0 privileges. The I/O manager loads the driver in this space and creates a driver object. And after that, it calls the driver entry routine, which is like the main function for the driver. And that driver entry routine initializes the rest of the thing, like all the callbacks that it's going to be used, like the dispatch functions, interrupt service routines, and everything. And it also creates a device object. That device object is the instance through which we, as a user mode application or another party, will connect to the driver. So when we actually talk to the driver, we are doing it through a device object. We create a handle to a device object, we read from a device object, we write to a device object, and by doing that, we are exercising the dispatch routines that the driver entry set, okay? And of course, a driver can manage more than one device. It can create more than one device object. Each one of those can have different ACLs. So we need to look at the ACL for each one of the device object that the driver creates. What we're looking here is device objects that, as a regular users without privileges, I mean, no non-administrative privileges, we can interact with, right? Those are the ones that we're looking for. So the driver entry calls this API, IO create device, to actually create a device object, and it passes. It has different fields. The one I wanted to highlight are the device name, but also the device characteristics. When you create a device object, every object comes with an associated namespace. And this is because every device object in Windows is actually treated as a file system, basically. And you have different paths in that namespace, of course. So unless you are a file system driver, you have to specify file device secure open in the device characteristic. Otherwise, you can get any user mode program open and a handle to your device bypassing your ACL because the system doesn't ensure the ACL on every part of the namespace. I'll get into that in more detail in a few slides, but this is bad. And I have seen several, in the past, in 2015, several antivirus systems deploy drivers with this not being said, and so you can do whatever you want back then. Well, the dispatch routines are the actual entry points. These are the code that are executed when you call create, read, write, or IO control. So this is the things that we are trying to get, to understand, to reverse engineer, and see how they work. There are different major functions codes, which a dispatch routine will treat differently. So, of course, the driver doesn't have to support all of them. But most of the time, the ones that we are interested in are the device IO control, read and write, things that we can control. This is the base code of a WDM driver. Basically, what it does is creates a device object with the API I pointed out before. Then it sets some dispatch handler routines. And then it creates a symlink. Creating that symlink allows user mode applications to open a handle to it. Otherwise, just another kernel mode component can interact with this driver. And if you look at the device characteristics, it's being set to null. So what that means is that if we talk to a driver from a user mode program, even if that driver set a strict ACL where only administrative users can open a handle, we can bypass that by just adding a // in the create file. Okay, just by adding that, we are saying that we want to access a part of its namespace, and given it's not file device secure open, we will get a handle. And there we have some functions like read file, write file, and device I/O control. That's how we interact with the driver. They receive different buffer sizes, but that's basically, it's mostly like a file, right? And with that, we are actually exercising the code that the driver set as dispatch routines. These are different syscalls that we can invoke, and on the left and on the right, we have the dispatch routines that we will exercise if are being set by the driver. There are a bunch of them. Some of them we have parameters that we control. We need to see what the driver actually does. Okay, and the dispatch routines work in terms of interrupt request packets, or IRPs. The IRP is created by the I/O manager upon we do a call. For instance, if we do a read, the read gets it enters into NTOS kernel. NTOS kernel creates the interrupt request packet, and then that is what we receive in our dispatch routine. The IRP has all the information necessary for the request, including the buffers and an array of stack locations. The stack locations are more information about that particular request. And we have a stack location for every driver in a layered architecture. So let's say we have a file system driver and also a filter driver from an antivirus. Whenever we want to read from a file system, we'll go through the filter driver first maybe, and then to the file system driver, right? Well, in that case, we have, of course, just a single IRP, but we have two stack locations, one for each driver. And each driver accesses its particular stack location to get the parameters, such as what's the size of the buffer, what's the I/O control code, etc. There are different forms that the driver can use to access the data in the buffers. So the first one, it's called buffered, in which when we send a request, for instance, I don't know, we want to write some data, the I/O manager takes that data, copies it into a kernel allocated space. So it's basically copying all the data into a new buffer, and that is the buffer that gets passed to the driver. So that's the most secure way. It actually, the I/O manager takes care of all the checks. But of course, it's slow if you have a lot of transfer. So then you have direct I/O. And in direct I/O, what happens is that the I/O manager locks your buffer, your user buffer, so you cannot unmap that memory. And then it creates another virtual address for that same physical page. So you have two virtual addresses pointing to the same physical page. And it's interesting because if the driver is not aware of that, you can change the data in the user mode program and have a race condition. If there are multiple reads from the buffer, nobody prevents the user mode program to change the data. It cannot unmap the memory, but it can change the data. So you can have race conditions there. And lastly, you have the neither method, in which the I/O manager doesn't get involved with the operation of the buffer at all. It just sends the user mode buffer, the address of the user mode buffer to the driver, and lets all this sanitization to the driver. So the driver has to check the length, has to check that the memory is mapped and everything. Of course, that method was the source of all the problems in drivers in previous years. How do you set the things? Well, for read and write and all those operations, you can set it in, you will see that is set in the device flags, device object flags. But for I/O control based operations, that's encoded in the I/O control code, which is the number we've seen before passing to the NT device I/O control. And it's just a combination of values that are packed into a D word. The interesting fields are the transfer type, which again indicates what kind of data transfer are we using, and the required access, which dictates what permissions your handle needs in order to issue that I/O control. And that's very interesting because you can sometimes find device objects that have something like that. You see the group everyone doesn't seem to have any operations. I mean, it seems to be able to open a handle with read permissions or with write permissions to that device. But you can pass null. And you can open a handle with no permissions, right? And that will return a handle. And what you can do is then start issuing I/O controls that are set with a transfer type, again, with a transfer type of file any access. And it will work. And the same is for things for read or write. In the end, you need to audit what access required is for each I/O control code. Of course, if you don't appear in the ACL, then you won't be able to open a handle. But if you see something like this, then you need to get into it. In WDM was very easy to find this stuff. You just open a driver in IDA Pro and you will see patterns like this, and you can be certainly certain that those are the dispatch routines. And what can go wrong here? A lot of things. You should check that presentation because really a lot of things can go wrong in WDM programming. And that's why they came with kernel mode driver framework. KMDF is just an abstraction on top of WDM. And because it's an abstraction, it's more difficult to understand what it's doing. New drivers are supposed to be written in KMDF, and device drivers and bus drivers are. Software drivers are not, for some reason, but it's difficult. It's more difficult because of this to get to the actual callbacks, and I'll show you in a demo why. So what happens is that KMDF sets its own dispatch routines for you. So he traps all the requests and then wraps those into better objects or more object-oriented, and you get, for instance, instead of IRPs, you get a request. Instead of having a dispatch routine, you have a callback for one queue. So what happens is that the driver creates a queue and sets different callbacks for those. For instance, callbacks when it comes a read request or a write request or device I/O control request. There's also a default, which actually gets called when there's no specific callback for reading, for instance. If I set null to read and I set the default, a read will get into the default one. That's interesting as well because I've seen some issues that I will show. A basic KMDF driver starts by creating the actual driver object. It calls that WDF driver create and specifies a callback, event device add, and that is what actually creates the device. And in here, file device secure open is set by default, so we don't need to worry about that namespace issue that we had before. And then it will create a queue. In this case, it's only setting the device I/O default. So all requests are going to be handled by that particular callback. And then it's creating a device interface. That device interface is what is similar to our symlink. Is what user applications can use or other components can use to open a handle to this device. It's setting a GUID, and we need to know that specific GUID in order to open a handle. So our actual driver entry, the code that you will see in the source code, you won't see that directly when you open your binary in IDA, because the KMDF library will wrap that and will call WDF version bind to us to do the binding of your driver to a specific version of the KMDF library. And with that, it will set a structure that specifies how many functions are, the version, and the pointer to a func table, which has all the callbacks, the KMDF callbacks that the driver that you're targeting is going to call later. We need to actually get into that and set at least those names, because otherwise we won't understand what the driver is doing. We just see different calls to different sections of the drivers, but we don't see the names, we don't see anything. And a device interface. So as KMDF, again, is mostly for device drivers and bus drivers, they cannot use names. They are using instead GUIDs. And we need to do another kind of steps to open a handle. We cannot just pass the GUID, of course, and as we don't have the name, we have to get it. Names like those. Okay, so for instance, the first one is the device path of the management engine driver. The second one is from one Intel audio driver. We need to get to pass that string to create file. Okay, how do we get that? Well, either by dynamically with WinObject, or by reverse engineering the driver, getting the GUID, and then using this code to get the actual device path. This is using the setup.di API of the OS, and that gets the actual device path that you need. Yeah, it's a mess, but it works. And one thing to note is that, I don't know why, but WinObject doesn't actually show you the reference string. So the reference string, in the case of the second device path, is that gray part there. And you need that. Again, when you do this, by default, you have OpenACLs for low privileged users. So unless they are setting a strict ACL, you can actually open a handle to the device. And even then, you still have to check any access of all the IO controls. Okay. And how does KMDF access the buffers? Before, they had to check the IO stack locations. Now, they get a request, and they can use this nice API to specify a minimum required length. And they actually get the actual length in the fourth parameter. And if you, I've seen seen drivers using this API in a bad way, because they either put that to 0, which is bad, or they put that to some value, but then they reference an offset that is beyond the minimum required length. So you can actually get an out of bounds read or write, depending on the operation. But yeah, and well, you have the same set of APIs for retrieving the output buffers, and in the case you are doing direct I/O, you also can do the second set, which are for MDLs. And for method neither, KMDF doesn't want you to use method neither. So if you really want to do this, you will see that you need to call those APIs like WDF request retrieve and save user input buffer. The name suggests to the developer that what they're doing is wrong, and it has to be called in a special context. So I haven't seen any driver using this really, at least a third party. About non-PNP, these are software drivers that do not manage a device. For non-PNP, what matters is that they set a special flag in the WDF driver config, and then they create a control device object. The control device object is pretty much the same as the normal device object that we know from WDM. They follow that flow. They create a control device init, and then they assign it a name. They create a device, create a symlink, creates a queue, and assigns an event handler to it, and that's it. What matters in here is the first call. WDF control device init allocate actually receives an SDDL string that specifies what are the permissions, what's the ACL. We can get that in the reverse engineering through IDA, get the SDDL string and use a tool like SDDL parse tool, like that. And we see that the string, the nasty string that is being passed to SDDL parse is, well, parsed, and we see that the everyone group is able to open a handle with read and write privileges in this case. So that's good. I will now show a quick demo of how everything is. Okay, so I have IDA Pro here. This is a AP filter. I don't have the symbols, of course. And I made this nasty script that will help us to put the names to get to the stuff that we care while we are reversing for bug hunting. Okay, so we're there. And you see, before actually executing the script, this is a driver entry. But if you see that this is actually the wrapper from KMDF. This is a call to WDF version bind. This is the structure WDF bind info. It has a version here. So our actual driver entry should be here, this one. And again, we see calls and calls, but we see things like this, right? We don't really know what it's doing. So it's difficult. By running this, well, it puts the names on it. Now we can more easily navigate through what I just described. Here's the driver add, so we can go here. And yeah, some IO control routine there. And it also outputs some information here. For instance, there is a control device SDDL at this location. So if we go there, we see an actual SDDL. If we do the xref, we see several instances of this being used. So that means several devices are being created. And for instance, in this case, we have here, this is the symlink. So apparently there is a device named a symlink called AP filter. And then it calls the device creates a symbolic link, and then it creates a queue, and it sets a device IO control here, right? So that's something we can look at. We need to parse that SDDL and see if we can open a handle, or we can do it dynamically, of course, but I'm showing the reversing approach. And in this case, now that we found this particular callback, we can go here, and we can start actually reverse engineering this, which if you see, it's pretty nasty and big. Okay, there's certainly there are likely to be bugs. And actually, if I'll show one quickly. Have it here. Sorry. Okay, have it here. It's comparing the IO control to this value, and if it matches, then it goes here, right? And calls this function. And if we go into this function, by looking at this, we get the idea of what this is doing. This is retrieving an output buffer. This is mapping memory that we can specify the address and size. And then it's calling this function. If we opened it, we see this is kind of mem copy, right? And then it's done. It's unmapping and returning that content. So this is basically arbitrary physical memory reading from user mode, right? Okay. Okay. About null buffers. In WDM, when you specify, when you call device IO control with null for buffer length or null, just a null buffer, you get the IRB system buffer and MDL address set to null. And if a driver doesn't check that, of course you get a blue screen. That still happens in 2018. I have some actual bugs related to that in NDIS. Not exactly that thing, but similar. But in the case of KMDF, it's no longer like that because you get, again, that nice API. And the first condition is that the minimum required length should be 0. Okay, so the developer should have set that to 0 so you can get a request to actually be read by the driver. The second thing is that even if that's set to 0, as we see in that case, the status from the callback is non-zero. So unless the developer also forgot to check the status, you will not get a null reference out of that. The code actually automatically states that when the length is 0, return the status buffer to small. And that's different than 0, so non-success. The same thing goes for read and write request. You have to have a queue specifying the allowed length request set to true, 0 length request set to true, and by default is false. So it's very hard to find those kind of issues. Now, null references of those kind are really hard to find. So what kind of issues we find? Well, we can find. Well, unsanitized data, like indexes, offset, pointers, Also, when the event IO default type is used, you can have a type confusion. Privilege operation exposed, that the one that I just showed, and like more things like registry keys, settings, IO ports reading and writing, which will mean bound, but just because of that. Object leakage, race conditions when using direct IO, and kernel pointer leakage in output buffers as well. That's pretty common. So this is a camera driver from Intel. You see that it's actually checking the length to be 648, and that passes. That's well. We pass a buffer which larger than that. But then what it's doing is taking the first D word and using it to construct an index and referencing directly. So that's bad. You have an out-of-bound reads there. Things like that are pretty common. KMDF won't save you there. So another thing that I saw is when using the event IO default callback, again, this is the callback that gets called by the framework when there's no another specific set, for instance, for reading or writing. And what I saw once is that a code path that got the IRP, get the buffer length, it just added 10, which was weird, and then calls a function that I call finish processing, which then took the buffer length and referenced that plus 28. So that basically took a length as a pointer. And I don't know, at first I didn't know what happened. Then I realized, okay, what happened is that they were expecting another kind of request. But by setting an actual IO control, you can get with the length there. And that's bad. Another kind of issue as well, I found that for bus drivers, in Windows, there is this sample code that you can have for base your driver, and you have this toaster driver that is public in the Microsoft GitHub. And I found that what the code was doing is exposing an API that allows you to add device objects to the bus driver. So the bus driver needs to enumerate devices, right? And on each enumeration, it passes the information to the plug-and-play manager that uses it to build the device tree. KMDF for this provides what is called a child list. And each time a bus driver identifies a child device, it must add the child device descriptions to the child list and then create a physical device object. That happens by calling that API there. Now, that API should be called in two situations. Now, first, when you have an interrupt, for instance, you plug a device, so the bus driver detects that should add a new instance of a child. And then when there is a device that enters its working state again after being asleep. So I found that in the Microsoft code, the sample code, they were exposing that operation as an IO control. So you can call it infinite times. The system will collapse because the object will start leaking. If you close your program, the object will still be there. So it's actually object leakage. If you open device tree, we'll see something like that. You have a parent device, and all those devices, that's thousands of devices created. Now, that's there. I saw some concrete implementations of this in Microsoft Virtual Wi-Fi bus driver, Intel Wireless Display as well, and some other gaming devices as well, gaming drivers. Not only that, but also when you have this implementation, your attack surface also increases, because as you can pass the identification description and address description, those structures are driver defined, you can end up attacking. You can attack the implementation of those calls down there. Those are the functions that the driver set in order to add the new child device to the child list. It has to parse what you specify in the identification description and address description. So it's more attack surface, basically. As an example of kernel pointer leakage, I have the Synaptics touchpad driver, syntp.sys. I saw this driver being used by some HP laptops, Lenovo, and also Acer. I don't know if other laptops use this, maybe. For all those IO control codes, they all return kernel pointers. So it was really bad. We informed this to Synaptics, they fixed it, but they then came back to us saying that not all OEMs are actually using the official update for different reasons. So if you have this, you should check your actual implementation. I couldn't check everything, of course. I have a video of this if you want to see it, so just a sec. So that's the device. This is I think it is a Bango machine. I don't know if it's known here. It's known in Argentina. And I'm showing now that any user can actually open a handle to the control device of Synaptics. Everyone has read and write permissions. So we just call it, right? And yeah, all of those are kernel pointers, valid kernel pointers. I have to stop because I mean it really leaks a lot. I don't know. Okay. Okay, how do you find this? It's easy. You just work for every binary you have as a driver and check that they are importing from that library. If they import a library, it's certainly a KMDF. And you can start analyzing it. So yeah, you will need to check your drivers. The third-party bus drivers are a good target, touchpad drivers as well. Camera, gamer devices, those are really good as well. So as a conclusion, KMDF, yeah, doesn't hate security by default. It by default sets file device secure open, no more of that ACL bypass that I showed before. No null buffers, unless you really want to. No null buffers. It also discards the use of method neither. There are better APIs to access the request and the informations, to check sizes, everything. So that's good. But there are many things that still can go wrong. Bad ACLs for device object because privileged operations are being exposed there and it shouldn't be accessed by regular applications, regular users. The data buffer, the data in the buffer should be treated carefully. And the APIs, even if they are better, they can be used wrongly, as I showed before. There can still be race conditions when using direct I/O, and well, they double check the content being written into the output buffers because we have things like that Synaptics touchpad driver we've seen. Well, those are the references, and that's all. If you have any questions.